What if I told you that the entire trillion-dollar AI arms race has been fighting the wrong battle? While tech giants have been burning through billions trying to accumulate more data, more compute power, and bigger models, a quiet revolution has been unfolding that completely flips the script. In the next 30 minutes, I'm going to show you why the future of artificial intelligence isn't about who has the most resources, but who has the deepest understanding of how to embed human wisdom into machines. This isn't just another AI trend analysis. This is about a fundamental shift that's already happening right now, particularly in one of the most challenging frontiers of AI, teaching robots to think and act in the physical world. And the implications go far beyond robotics. They touch every industry, every economy, and ultimately, how we'll work and live in the coming decades. So whether you're an entrepreneur trying to figure out where to place your bets, an investor searching for the next paradigm shift, or simply someone who wants to understand where this technology is really heading, stay with me. Because what you're about to discover will change how you think about the AI revolution entirely. Let's start by understanding what's actually broken in how we've been approaching AI development. For years, the dominant philosophy has been beautifully simple and brutally expensive: throw more data at the problem. The logic seemed unassailable. Language models got better when trained on more text. Image recognition improved with more labeled photos. So naturally, the path forward was clear. Whoever could accumulate the most training data would win the AI race. This led to an escalating arms race where companies competed on who could scrape more of the internet, who could generate more synthetic data, who could afford more compute hours to process it all. But here's where it gets interesting. This brute force approach works reasonably well when you're dealing with digital information that already exists in massive quantities online. Text, images, videos, they're all out there waiting to be harvested. But what happens when you move from the digital world into the physical world? What happens when you need to teach AI systems to manipulate objects, to understand physics, to complete tasks that require interacting with three-dimensional reality? Suddenly, the data problem becomes exponentially harder. You can't just scrape physical world data from the internet. Sure, you can watch videos of people doing tasks, but that's fundamentally different from the embodied experience of actually performing those tasks. To generate real physical world training data, you need actual robots, performing actual tasks, collecting data point by data point. And the numbers here are sobering. Using traditional teleoperation methods, where humans control robots to demonstrate tasks, you might collect 200 to 300 data points per day if you're working efficiently. That's it. Now think about what you'd need to achieve true generalization, the ability for a robot to handle any object, any task, any scenario. You'd need millions, possibly billions of data points covering every possible variation. At 200 to 300 points per day, we're talking about timescales that stretch into decades, maybe centuries. The math simply doesn't work. The brute force approach that powered the language model revolution hits a brick wall when confronted with physical reality. This is where a completely different philosophy emerges, one that's been proven spectacularly by recent breakthroughs. Instead of trying to compensate for lack of understanding with sheer volume of data, what if you could embed deep human knowledge directly into how the models learn? What if you could encode decades of robotics expertise, physics understanding, and manipulation principles right into the architecture and training process itself? Think about how humans learn compared to how we've been training AI. When a child learns to stack blocks, they don't need to see 10,000 examples of block stacking. They develop an intuitive understanding of gravity, balance, object permanence, and spatial relationships. These fundamental principles allow them to generalize from just a handful of examples to infinite variations. They understand that what works with blocks will also work with books or boxes, or any other stackable objects. That's knowledge-driven learning, and it's incredibly efficient. Now let's go deeper into why embodied AI represents such a unique and difficult challenge, because understanding this is crucial to appreciating the breakthrough we're discussing. When we talk about embodied AI, we're talking about artificial intelligence that doesn't just process information but physically acts in the world. This is the difference between a language model that can write about making coffee and a robot that can actually make coffee. The challenges here are profound and multi-layered. First, there's the generalization problem across what we might call three critical dimensions. The first dimension is the subject, the robot itself. Industrial robotics has traditionally been highly specialized. You have one robot designed for welding, another for painting, another for assembly. Each robot is purpose-built with specific hardware for specific tasks. But imagine if you could create a model that works across radically different robot forms. A model that could control a simple two-fingered gripper, or a sophisticated multi-digit dexterous hand, or even completely different robotic platforms. That's subject generalization, and it's essential if we want robotics to scale beyond narrow industrial applications. The second dimension is object generalization. The physical world contains an infinite variety of objects with vastly different properties. Rigid objects like bottles and boxes behave completely differently from deformable objects like fabric or rope. Fragile items require gentle handling. Heavy items need different force profiles. Temperature-sensitive materials add another layer of complexity. Traditional robotics handles this through specialized programming for each object type. You want a robot to handle a new object? You write new code. But true generalization means a robot can encounter a novel object it's never seen before and still manipulate it successfully by understanding its fundamental properties. The third dimension is predicate generalization, essentially task generalization. Can the system handle not just simple pick-and-place operations but complex, multi-step tasks that require planning, adaptation, and problem-solving? Can it assemble furniture by reading instructions? Can it tie a knot? Can it fold clothes? These are tasks that involve long sequences of actions, continuous adjustment based on feedback, and the ability to recover from errors or unexpected situations. But here's what makes this even more challenging. The physical world doesn't forgive mistakes the way the digital world does. If a language model generates a wrong word, you can just generate another one. If a robot drops a fragile object or applies too much force and breaks something, there are real consequences. The system needs to understand physics at a deep level: friction, momentum, center of mass, material properties, all the things that govern how objects behave in reality. And this brings us to perhaps the most fundamental challenge: the data gap. Large language models were trained on essentially the entire written internet, trillions of words of text. But there is no equivalent repository for physical interaction data. Yes, there are videos online of people performing tasks, but videos are fundamentally limited. They show you what's happening from a visual perspective, but they don't capture the forces involved, the tactile feedback, the precise motor commands needed to execute actions. This is where we arrive at one of the most ingenious solutions to the embodied AI data problem: simulation. But we're not talking about simple virtual environments here. We're talking about physics-accurate simulation engines that can generate what I call physically precise data, the missing ingredient that bridges the gap between digital AI and embodied AI. Let me explain why this matters so much. When you train a language model, you're fundamentally teaching it patterns in language, how words relate to each other, how concepts connect, how to predict what comes next in a sequence. But when you train an embodied AI system, you need to teach it not just visual patterns but physical laws. The model needs to internalize concepts like gravity, inertia, elasticity, friction. It needs to understand that pushing something harder makes it move faster, that objects fall when unsupported, that flexible materials behave differently than rigid ones. Now, you could try to learn all of this purely from real-world data, but remember our data collection problem. Or you could create simulation environments that accurately model physics and generate unlimited training data within those environments. This is what's happening at the cutting edge right now. Advanced simulation engines can create virtual scenarios where robots interact with objects under realistic physical conditions. And because it's simulation, you can generate thousands or millions of these interactions, covering edge cases and variations that would be impractical to collect in the real world. But here's the critical insight: the simulation itself must be built on deep human knowledge of physics and robotics. You can't just throw together a random virtual environment and expect useful training data. The simulation engine needs to accurately model real-world physics, material properties, sensor characteristics, actuator dynamics. This requires embedding decades of physics research and robotics engineering knowledge into the simulation framework itself. And this is where we see the knowledge efficiency principle in action. Instead of trying to learn physics from scratch through millions of real-world trials, you encode physical laws directly into the simulation. Instead of hoping the model will eventually figure out optimal grasping strategies after countless attempts, you build simulations that reflect human understanding of manipulation principles. You're not replacing learning with hard-coded rules. You're providing a foundation of knowledge that makes learning dramatically more efficient. The beauty of this approach is that it creates a virtuous cycle. The simulation generates training data. The model learns from that data and improves. The improved model's performance in real-world tests provides insights that refine the simulation. The refined simulation generates better training data. And the cycle continues, with each iteration building on human knowledge rather than trying to rediscover fundamental principles through brute force. Moreover, advanced simulation enables something incredibly powerful: the ability to learn from human demonstrations at scale. A person can demonstrate a task in the real world, and that demonstration can be recreated and varied thousands of times in simulation. So a single human demonstration of folding a shirt can become 1,000 variations of folding different shirts in different states. This multiplies the value of human expertise exponentially. Now let's explore another fascinating dimension of this knowledge-efficient approach: teaching robots to learn from video. This might sound simple at first. After all, we have millions of videos online showing people performing tasks. But extracting actionable robotic knowledge from video is extraordinarily complex and represents another area where embedding human knowledge makes all the difference. When you watch a video of someone assembling furniture, your brain is doing incredible computational work that you're not even aware of. You're inferring three-dimensional structure from two-dimensional images. You're understanding which hand movements correspond to which effects on the objects. You're recognizing when the person is applying force, estimating how much force, understanding the sequence and purpose of each step. You're essentially reconstructing a rich model of the physical interaction from limited visual information. For an AI system to do the same thing requires sophisticated understanding built into the model architecture. The system needs to understand visual cues that indicate force, the way fingers compress, the tension in materials, the acceleration of objects. It needs to understand spatial relationships and how they change over time. It needs to parse complex sequences into meaningful subtasks and understand causal relationships between actions and effects. Here's where knowledge embedding becomes crucial again. You could potentially train a massive model on millions of hours of video and hope it learns these principles through pattern recognition. But embedding knowledge about physics, about how humans manipulate objects, about the relationship between visual cues and physical forces, this dramatically reduces the amount of video data needed and improves the quality of what's learned. Think about it this way: if the model already understands that objects fall downward due to gravity, it can make much better sense of videos where objects are released or supported. If it understands that rotational movements correspond to turning actions, it can more efficiently learn from videos of people opening jars or turning knobs. The embedded knowledge acts as a powerful prior that guides the learning process. But the real breakthrough comes when you can combine multiple learning modalities. Real-world human demonstrations provide rich tactile and force information but are expensive to collect. Videos provide visual information at scale but lack physical detail. Simulation provides unlimited physically accurate data but requires validation against reality. When you can integrate all three, learning from each and using embedded knowledge to translate between them, you create a learning system that's far more powerful than any single approach. This multimodal learning approach also enables something particularly exciting: the ability to follow natural language instructions. If your model understands both language and physical tasks, it can receive instructions like, "Assemble this furniture according to the manual," and actually execute that task. This requires understanding abstract symbols in the manual, translating them into physical actions, and adapting when things don't go exactly as depicted. It's an integration of language understanding, visual perception, spatial reasoning, and motor control all working together. Now I want to connect all of this to a recent development that has sent shockwaves through the AI industry and validated this entire knowledge-efficient approach: the emergence of DeepSeek and what it represents. DeepSeek isn't important just because it's another capable language model. It's important because of how it was built and what that demonstrates about the future of AI development. The traditional narrative around AI progress has been that advancement requires ever-increasing resources. More data, more compute, bigger models, larger teams, massive capital investment. The subtext was that only the wealthiest companies could compete at the frontier of AI development. But DeepSeek challenged that narrative fundamentally by achieving comparable performance to models trained with vastly more resources. How? By embedding deep understanding of model architecture, training dynamics, and optimization techniques into every aspect of development. This is the same principle we've been discussing for embodied AI, just applied to language models. Instead of compensating for limited understanding with unlimited resources, DeepSeek demonstrated that deep knowledge enables you to do more with less. They didn't just throw data at a model and hope for the best. They carefully architected their approach based on understanding what actually matters in model training, what data is most valuable, how to optimize the learning process. The implications of this are profound and extend far beyond language models. DeepSeek proved to the world, to investors, to policymakers, to entrepreneurs, that the knowledge-efficient approach isn't just theoretically superior, it's practically viable. It shifted the conversation from, who has the most resources, to, who has the deepest understanding. And that's a conversation where innovation can come from anywhere, not just from the handful of companies with the deepest pockets. For robotics and embodied AI specifically, this validation is crucial. Building advanced robotic systems requires significant capital, but the DeepSeek moment demonstrated that clever, knowledge-driven approaches can compete with and even surpass brute force methods. This opens the door for more companies, more researchers, more innovation in the space. It redirects capital toward teams that demonstrate genuine technical understanding rather than just resource accumulation. But there's another critical dimension here that goes beyond pure technical validation. DeepSeek captured attention, and in the modern economy, attention might be the most valuable resource of all. By demonstrating this knowledge-efficient approach so dramatically, DeepSeek focused global attention on this methodology. Suddenly, investors are asking different questions. Engineers are thinking differently about problems. The entire industry conversation has shifted. This attention shift matters because it creates a feedback loop. More attention means more talent flowing into knowledge-efficient approaches. More talent means faster progress. Faster progress generates more attention. And we're seeing this play out right now across multiple domains of AI development. Let me close by zooming out to the bigger picture of what all of this means for the global AI landscape and where we're heading in the next 5 to 10 years. Because the knowledge-efficient revolution isn't happening in a vacuum. It's unfolding against a backdrop of geopolitical competition, different innovation ecosystems, and fundamentally different approaches to technology adoption. One of the most fascinating dynamics is how different societies embrace and integrate new technologies. Some societies have experienced decades of rapid technological change and have populations that readily adopt new tools and platforms. This creates vibrant experimental environments where AI applications can be tested, refined, and scaled quickly. The feedback loops between developers and users are tight and fast. This matters enormously for AI development because these systems improve through interaction and deployment, not just through lab testing. The complexity and diversity of different markets also creates unique advantages for AI development. When you have industries and use cases that might not exist elsewhere, you create opportunities to push AI into novel domains. Traditional sectors that might seem resistant to technology in some contexts become unexpected proving grounds for advanced AI systems. This diversity of application scenarios generates diverse training data and drives innovation in ways that more homogeneous markets cannot. Looking ahead, the vision for AI-powered robotics is truly transformative. We're not talking about robots as tools in the traditional sense, but as something closer to coexisting entities that work alongside humans. Imagine a future where robotic systems are as commonplace in homes and workplaces as smartphones are today. Not replacing humans, but augmenting human capability, handling physical tasks that are dangerous, repetitive, or simply time-consuming. But achieving this vision requires continuing down the path of knowledge efficiency we've been exploring. The robotic systems of the future will need to be generalizable enough to handle unpredictable home environments, safe enough to work closely with people, and intuitive enough that anyone can direct them with natural language. This level of capability cannot be achieved through brute force data collection. It requires embedding deep understanding of physics, safety, human behavior, and common sense reasoning into the models. The international dimension of this development is also critical. The most rapid progress will come from collaboration and knowledge sharing across borders, bringing together the algorithmic innovations, hardware capabilities, and diverse application environments that different regions offer. The tendency toward viewing AI development as zero-sum competition between nations is ultimately counterproductive. The breakthroughs that matter most, the ones that will define how AI shapes human civilization, will benefit from the widest possible collaboration. As we stand at this inflection point, the key takeaway is this. The AI revolution's next phase will be won not by those with the most resources, but by those with the deepest understanding of how to embed human knowledge, wisdom, and values into these systems. The shift from brute force to knowledge efficiency isn't just a technical optimization. It's a fundamental reorientation of how we approach building intelligent systems. And it's a shift that opens up the field to more participants, more innovation, and ultimately, better outcomes for everyone. The robots and AI systems that will transform our lives in the coming decades are being built right now, not by simply accumulating data and compute, but by thoughtfully encoding human understanding into every layer of these systems. That's the revolution, and it's just beginning.